In this lesson, we will delve into the principles of gear machining and tool technology from Project 1, focusing on gear shaping and gear shaper cutters. Gear shaping is an important method of gear machining, and the gear shaper cutter is the key tool for this process. We will explore the principles and the characteristics of gear shaping, as well as the structure, types, and the design of gear shaper cutters. Additionally, we will analyze the precision mechanical design concepts involved, appreciating the charm of traditional craftsmanship. Gear shaping is a process that uses the generating method principle to machine gears. The generating method, also known as the enveloping method, is a technique that uses the meshing motion of a gear pair to cut the gear tool's profile. In gear shaping, the gear shaper cutter acts like a gear with cutting edges. It meshes with the gear being machined at a specific transmission ratio, gradually cutting the tool's profile into the workpiece. From the perspective of motion, gear shaping primarily involves the following types of movement. 1. Main motion, the up and down reciprocating linear motion of the gear shaper cutter, which is the primary source of cutting power. The speed of the main motion is usually expressed in terms of the number of reciprocating strokes per minute, denoted as NR strokes min. 2. Indexing motion, the meshing motion between the gear shaper cutter and the gear being machined. The indexing motion ensures that the rotational speed of the workpiece N work and the rotational speed of the gear shaper cutter N cutter satisfy the relationship N work divided by N cutter equals Z0 divided by Z, where Z0 is the number of teeth on the gear shaper cutter, and Z is the number of teeth on the workpiece. This ensures the correct tooth profile is cut. 3. Circular feed motion, the rotational movement of the gear shaper cutter around its own axis. This determines the feed amount for each cut, expressed as the arc length traversed on the pitch circle per reciprocation of the cutter, denoted as FC yen per stroke. 4. Radial feed motion, the radial movement of the gear shaper cutter towards the center of the workpiece, allowing the cutter to gradually penetrate the workpiece until the required tooth depth is achieved. The radial feed amount Fr is typically expressed as the distance the cutter moves radially per reciprocation mm per stroke. Relief motion, to prevent the gear shaper cutter from rubbing against and damaging the machined surface during the return stroke. The cutter must move away from the workpiece. This is known as the relief motion. High machining accuracy. Since gear shaping utilizes the generating method principle, it ensures the accuracy of the gear tooth profile and indexing. Generally, the machining accuracy of gear shaping can reach levels 7 to 8 with a surface roughness of Ray 1.6 to 3.2 micrometers 2. Capability to machine internal gears. This is a significant advantage of gear shaping. For internal gears, methods like hobbing are difficult to implement, whereas the gear shaper cutter can easily enter the tooth slots of internal gears for machining 3. Ability to machine cluster gears. When machining cluster gears is required, gear shaping can complete the machining of multiple gears in a single setup, ensuring positional accuracy between the gears. 4. Relatively low productivity. The main motion of the gear shaper cutter is the reciprocating linear motion with no cutting occurring during the return stroke. Additionally, the cutting edge length of the gear shaper cutter is limited, and the material removed per cut is small. Therefore, the productivity of gear shaping is relatively lower compared to methods like gear hobbing. The structure of the gear shaper cutter. A gear shaper cutter generally consists of the cutter body, cutting edges, and chip pockets. The cutter body serves as the base of the gear shaper cutter, ensuring its strength and rigidity. The cutting edges are the critical part of the gear shaper cutter, as their shape and precision directly affect the tooth profile accuracy of the machined gear. The chip pockets are used to accommodate the chips removed during cutting, ensuring the smooth progress of the cutting process. 1. Disc-type straight-tooth gear shaper cutter. This is the most commonly used type of gear shaper cutter, primarily used for machining external gears and large diameter internal gears. It has a simple structure, making it easy to manufacture and sharpen. 2. Bow-type straight-tooth gear shaper cutter. Shaped like a bow, this cutter is mainly used for machining cluster gears and gears with shoulders. Its slender neck helps avoid interference with the workpiece's shoulder during machining. 3. Taper shank straight-tooth gear shaper cutter, suitable for machining small diameter internal gears. It connects to the machine spindle via a taper shank, allowing for easy installation. The design of a gear shaper cutter needs to consider multiple factors to ensure that the machined gear meets the required specifications. 1. Tooth profile design. The tooth profile of the gear shaper cutter should be designed based on the tooth profile of the gear being machined, typically using an involute tooth profile. The involute profile offers good transmission performance and manufacturability. When designing the tooth profile, parameters such as the cutter's addendum height, dedendum height, and tooth thickness must be considered, as these will affect the tooth profile accuracy and meshing performance of the machined gear. Selection of tool material. The gear shaper cutter must withstand significant cutting forces and cutting heat during operation, so the tool material should possess high hardness, wear resistance, and thermal hardness. Commonly used tool materials include high-speed steel and cemented carbide. High-speed steel offers good cutting performance and workability, making it suitable for general gear shaping. Cemented carbide, with its higher hardness and wear resistance, is suitable for machining harder materials or for high-speed cutting. 3. Determination of tool geometric parameters. The geometric parameters of a gear shaper cutter include the rake angle, relief angle, and the cutting edge inclination angle. The rake angle, gamma 0, can reduce cutting force and cutting heat, thereby improving the cutting performance of the tool. However, an excessively large rake angle may decrease the tool's strength. The relief angle, alpha 0, can reduce friction between the tool and the workpiece, enhancing the tool's lifespan. The inclination of the rake face, together with the helix angle of the chip pocket, determines the chip flow direction, thereby improving cutting conditions. Gear shaping is widely used in the field of mechanical manufacturing. In industries such as automotive, machine tools, and aerospace, many gear components are manufactured using gear shaping. For example, internal gears and cluster gears in automobile transmissions, due to their high precision requirements and complex shapes, are often produced through gear shaping to ensure machining quality. The classic method of gear shaping embodies a wealth of precision mechanical design concepts. The application of the generating method principle reflects the wisdom of our predecessors, achieving high precision gear machining through ingenious mechanical movements. In modern manufacturing, although many advanced machining technologies have emerged, traditional processes like gear shaping remain indispensable foundations. We must carry forward these precision mechanical design concepts while also innovating based on traditional techniques. For example, by improving the materials and coating technologies of gear shaper cutters, we can enhance their cutting performance and lifespan. Additionally, utilizing computer-aided design and manufacturing technologies allows us to optimize the process parameters of gear shaping, thereby increasing machining efficiency and precision. In this lesson, we primarily learned about gear shaping and the related knowledge of gear shaper cutters. We first understood the principles of gear shaping, including the main motion, indexing motion, circular feed motion, radial feed motion, and relieving motion. We then discussed the characteristics of gear shaping, such as its high machining precision and capability to machine internal and cluster gears, though with relatively low productivity. Next, we introduced the structure and the types of gear shaper cutters, including disc type, bowl type, and taper shank straight tooth gear shaper cutters. We also covered the design of gear shaper cutters, including tooth profile design, tool material selection, and the determination of geometric parameters. Finally, we emphasized the craftsmanship inherent in traditional processes like gear shaping, recognizing that these traditional techniques are the foundation of modern manufacturing, and we must both preserve and innovate upon them. I hope that through this lesson, everyone has gained a deeper understanding of gear shaping and gear shaper cutters.